how do we calculate an empirical formula? So we're going to look at this example. A gaseous compound containing carbon and hydrogen was analyzed and found to consist of 83.65% carbon by mass. Determine the empirical formula of the compound. So the first step in finding the empirical formula is to obtain the mass of each element present. So in our experiment, we came up with masses because we measured the magnesium, the mass of it on the balance, and we measured the magnesium oxide, and then by subtracting we could get the mass of the oxygen. Here we're given a percentage, and they don't tell us how big the sample is. So what do? Well, we make some assumptions, and we do so in a way that makes life easier for ourselves. So if they give you a percentage, then just assume a sample size of 100 grams. If we had a sample size of 100 grams and it was 83.65% carbon, how many grams of carbon would there be? 83.65, right? That makes life easy. So when you assume a 100-gram sample, then the percentage is the same as the mass in grams. So if they give you a mass in grams, just don't write the percent, write gram instead. And so here we've got 83.65 grams of carbon. But there's another element in there, right? Hydrogen. What's the mass of the hydrogen? It must be 100 minus that. Because there's only two elements, and if the sample's 100 grams and 83.65 of that is carbon, then the other 100, the rest of it must be the hydrogen. 16.35?
Yeah, I just looked at it.
Thank you.
I think so.
Grams of hydrogen. Okay, so that's the first step. Mass in grams. The next step is to find the number of moles. Because a chemical formula relates the number of atoms. So it's talking about particles. And so grams don't relate to particles, but moles relate to particles. A mole, as a chemist, doesn't. It's a counting number. So we're going to take those masses and we're going to find the number of moles. And we do that by using the molar mass of those compounds. And we learned how to do this last week. So we have grams of carbon, and we want moles of carbon. So we're going to multiply by moles of carbon, and we're going to divide by grams of carbon. The relationship between grams and moles comes from the periodic table. Here there's no formula because this is an element, not a compound. So we just look up under C, it says 12.01. So that's our number right here. So we did this in the way that the units cancel out because the units are our friends and they help us know what to do. 83.65 divided by 12.01. 6.965 moles of carbon. Now just a word about significant figures. What are we trying to find out here? We're trying to find the empirical formula. That's going to have whole numbers in it, okay? And so there's no significant figures in our answer. And yet significant figures are still important because if you drop your significant figures, if you just lose them and throw them away along the way, you're going to introduce rounding errors and you can come up with the wrong formula. So when you're doing this, be sure to include at least the correct number of significant figures. And if you want to throw some more in there, more is better. Okay, if you round, like if you take this number and you round it off to 7, you could end up getting the wrong answer. And I see that happen a lot. Students will round off when they really shouldn't be. So then grams of hydrogen to moles of hydrogen, same process. We look up hydrogen in the periodic table, we get 1.008. So 16.35 divided by 1.008. I'm just using the numbers from the periodic table that I give you on exams, which are rounded to 4 sig figs. If you use other ones, you'll be fine. 115.14 moles of hydrogen. So converting grams to moles is a super important type of calculation. You got a different answer? Okay. Yeah.
Did you use 1.01?
16.35 divided by 1.008. Yeah, I just screwed up. It happens. And it's Monday, so it's going to happen even more today, right? Yeah, I'm getting 16.22 now. Is that what you got?
Yeah.
Thank you for correcting me. That's why you always do it twice. Any other questions? So that's the second step, convert to moles. Because now we can look at the relationship between particles, and that's what we need. So there's our number of moles that we just calculated. We need a whole number ratio. And so what we're going to do is we're going to take both of these and we're going to divide them by the smallest. Because what we could write, I'll write it up here on the top. We could say that our formula is C, whoops, changed the slide, didn't mean to do that. Okay, sorry about that. We could say that our formula is C with a subscript of 6.965, H 16.22. That's not a very good chemical formula, is it? We need those numbers to be whole numbers. So the way we do this is we take and we look at these two numbers of moles and we're going to divide by the smallest. Well, 6 is smaller than 16. So we're going to take this one and we're going to divide by 6.965, and that one's going to come out to be 1. One of these will always come out to be exactly 1 because you're dividing something by itself. And we'll take this one and we'll divide by 6.965. So 16.22 divided by 6.965. And you get 2.329. Is that a whole number? No. Is it really, really, really close to a whole number? No, not really. So this is my just kind of a guideline of when to round, because especially when you're doing this with an actual experiment or real experimental data, not made up data, it's not going to come out to be exactly 2 or 3 all the time. It's maybe going to come out to be 2.0473 or something, and then you have to decide, well, should I round that or not? So if it's less than 0.2 from a whole number, then you can round it. So what does that mean?
Don't round it.
That means don't round it. So what's the closest whole number to 2.329? The closest whole number is 2, right? So if we take 2.329 and we subtract the nearest whole number, we get 0.329. That's bigger than 0.2. You cannot round it, okay? because you'll end up with the wrong formula. So then what do? Okay, last step. If you don't end up with whole numbers or numbers that you can round, then you multiply by the smallest integer that will convert all of them to whole numbers. And so there's two ways to approach this. Now, they rounded the 2.329 to 2.33, which I don't recommend doing, but in fact, I'm going to fix it.
So we leave it at 2.329?
Yeah, you should really keep it at 2.329. They're being sloppy. So one way to do this is to recognize the decimal equivalent of fractions. 0.5 is equivalent to what fraction? 1/2. And 0.25 is equivalent to 1/4, right? 0.33 is 1/3. So if you recognize those, great. You can say 0.329, that's really close to 1/3. I bet if I multiply by 3, I'll get a whole number. If you don't recognize that, you can use the trial and error method, and that's the one I'm going to do because that's what most of the students end up doing. So I'll try multiplying this by 2 and seeing what I get. So I go times 2, and I get 4, that's not a 4, 4.658. Is that close enough to round? No, it's not. So that didn't work. So then I'm going to try 3. So what you do is just you try 2. If 2 doesn't work, you try 3. If 3 doesn't work, you try 4. That's the trial and error method. So I'm going to try 3. 2.329 times 3. 2.329 times 3. Okay, this comes out to 6.987. Is that within 0.2 of 7? Yeah, it is. So I can round this. This is approximately equal to 7. I can round that off to a whole number. But if I want my ratio to stay the same, I had a ratio of 1 to 2.329. If I want the ratio to stay the same, I have to multiply both of them by the same number. So if I multiply this one by 3, I have to multiply this one by 3. And these are the numbers that end up being the subscripts. So I get C3H7.
Did you have another number with another element with another number that was goofy when you multiplied it through
It's possible, yeah.
So
Could you have, like if you had 3 elements, and you multiplied by 3, and you got one of them to straighten out, but the other one's still screwed up, yeah, then you have to keep going up. We won't do that to you in this class. You're welcome.
in this class?
Is it like for mathematical to do that mathematically? Is that like, would that be similar to like these common denominators?
A little bit, yeah. So you've got this ratio of 1 to 3.29,
Yeah, because you're
and you're multiplying by 3 over 3, and you get 3 over 7.
okay.
It's just a technique to get whole numbers from not whole numbers. Okay? Any questions? This is the process you need to do on the data you got in lab. So you have a mass of magnesium and a mass of oxygen. You convert them to moles of each. You find the smallest number of moles. You divide both of them by that smallest number. And now you've got one of them will be exactly 1, and the other one will be something else. If it's within 0.2, you can round it. If it's not, then you need to multiply both of them by the same number. So I think we have an example coming here. So here's another example. The composition of adipic acid is 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen by mass. What is the empirical formula? So we're going to convert those percentages to grams, to masses. And we do that by, it's just so beautifully simple. 49.3% becomes 49.3 grams. And we can do that because we're just assuming a 100-gram sample. The percentages are the same no matter what size sample we choose. And so we just chose something that was easy. So then we have 6 6.9 grams of hydrogen and 43.8 grams of oxygen. We're going to convert these to moles. We multiply by moles of carbon. We divide by the molar mass, 12.01 grams of carbon. This one, multiply by moles of hydrogen, divide by the mass, 1.008 grams of hydrogen. And here's oxygen times 1 mole, divide by 16.00 grams of oxygen. (49.3) divided by 12.01. And again, do not over round your numbers. 4.1. Now, we started out with 3 significant figures here, and so I'm going to call this 41.05 just because. I'm just going to keep an extra one. So that's moles of carbon.
Do you want us to keep an extra one?
I think it's a good idea to carry extras
For imperial?
for the empirical formulas, yeah. Carbon ends up being 6.845 moles of hydrogen. I mean, if you want to, you can write down all the digits that your calculator gave you. You don't have to, but it won't hurt here, because we always round off at the end, and here there's going to be nothing to round off. I'm just going to write all of that because that's all it showed me. That's kind of big. 2.737 moles of oxygen. So we found the grams, we convert to moles. Now we identify which of those numbers is the smallest. It's the 2.7, and we divide all of them by that. So we're going to divide this by 2.7375, and that one will end up being 1. So one of them always ends up being 1. And divide this one by 2.7375, 6.845, divided by 2.7375. That one comes out to be 2.5005. I throw those out, extra digits out there, just to show you that it came out really so close to 2.5. .105 divided by 2.7375. And this one comes out to 1.4995. So the oxygen came out to be 1, and the hydrogen is 2.5, and the carbon is 1.4995. Neither of those can be rounded to a whole number. So we have to multiply all of them. And perhaps you recognize that both of those 1.4995 and 2.5005 are really close to having 0.5, which is 1/2. And so when we multiply this by 2, we get 2.9999. Okay, so that ends up being 3. And when we multiply this by 2, we're going to get 5. And then we have to multiply this one also by 2. Because if we don't multiply all of them by the same number, we change the ratio, and the ratio is what we need. So we multiplied by 2, we got whole numbers, and so we get C3H5O2. That's the empirical formula for adipic acid. Any questions? Makes sense? Yeah, the individual steps are not difficult. The hard part is remembering the steps. Okay? And part of that will come just by doing some examples and some problems on your own. And when you've done it enough times, then you'll remember it. I went to Iowa State University for my undergrad, and they put in, I think they had redid the lawn or something. Anyway, there's this big green area, and they didn't put any sidewalks in at first. And so, because college students really, they'll walk on sidewalks if it's convenient, but otherwise they just walk across the grass, right? So what they did is they just left it all grass for quite a long time, and then eventually what we call in Iowa cow paths would show up. Because the students would tend to walk, straight from this place to that place, and they'd walk in the same place, and they would make a path in the grass because they had been over it so many times. And then they put the sidewalks where the students walked. How's that for smart? Yeah. And then nobody walked on the grass because nobody wanted to walk on the grass because the sidewalk was where they wanted to walk. And how does that apply to this? Your brain is a little bit like the grass, like the lawn. If you walk over your brain and do this problem once or twice, you may bend the grass blades, but the grass is going to pop back up, and pretty soon there's going to be no record of that having happened. If you do it over and over and over again, you'll compact the dirt in your brain, and the grass won't grow there anymore, and you'll remember where the path is. So some of these things, you just have to do them repetitively enough that you remember them. Or make a flashcard and list out the steps. Find the grams, convert the grams to moles, divide by the smallest number of moles, multiply by an integer to get a whole number. If that makes sense to you. Sometimes steps like that, you're like, well, yeah, I remember the steps, but I don't know how to do them. Okay, that's another problem. Okay, so this is calculating empirical formulas.